So, so I've written up on the board as usual the topics, or some of the main topics for this lecture. It certainly will connect to the next one. So this is least squares, estimation, and so I'm interested here in weighting, in the weighting matrix, the role of the covariance matrix, and in the recursive part. But the number of parameters, the parameters I'm looking for, u hat, well, I'm looking for u and I settle for u hat, is not changing. I mean, is improving, but we're at a fixed time, so to speak. So we've got these various steps. Least squares. Hi. I think I started a moment early, but I've written. I haven't said anything yet that isn't already written. So this we know about. This weighting matrix I'll introduce early, and then this recursive aspect. So those are the themes of this lecture, and then on into the next lecture will come a dynamic problem in which the u that we're looking for is changing. So, you know, something is moving. We're tracking a missile. Whatever we're doing, we know something about the connection between the present state and the previous state, but they're not the same. Okay. And may I say, I regret that Kalman's name starts with K, because I've been using K so widely for our A transpose CA matrix. But maybe today I'll tend to write out A transpose CA or A transpose sigma inverse A. That will be the matrix C that's appropriate. So I'll stay with, of course, the world convention that K stands for this gain matrix named after Kalman, and I'll come to that. Maybe can I say just a few words in advance before I start? Well, one, I want to say a few final things about the SVD, or maybe not final, but a few, just a supplementary, like a short recap, partly because I feel it's always good for the previous lecture to kind of come back again at the start. Secondly, to say that this area is, well, first to say that I'm not an expert in it, and that I had a wild time this morning. I feel I left home with a head packed full of formulas for the Kalman filter, and but the formulas are quite wonderful. And I'll try to organize them here. But I just have to say that every exposition of the Kalman filter has its own way of reaching these formulas, and they always seem confusing. And then the next person tries his or her own way and feels, okay, now I've finally got it all clear. But of course the next reader says, not the best way, and do it again. So that applies to myself too. So there's just a little about the Kalman filter in the course textbook, the applied math book. Then the latest book that I got involved with was was this one with my friend Kai Bore. It starts with linear algebra, so those chapters are very familiar. His subject is geodesy. And then the third part of the book is about GPS, global positioning. Well, for that, filtering is highly important. So I had to learn about the Kalman filter, and the final chapter of that book is now, or will be this afternoon or early tomorrow morning, on our website. So I felt I wanted to give you, since we couldn't get all the board isn't big enough for all the formulas of the Kalman filter, but So that's this chapter 17, Kalman filters from that book, is on the website. And really it expresses my starting point. So what should I say about that? And I say it here. There are several ways to start on the Kalman filter. People who are in statistics think of it as regression. People who are in probability think of it as conditional probability. And those two, which from a distance seem like they should be able to talk to each other, I can see in the early literature many references to people who had to translate, of course, the main ideas into their own world, so that all these different worlds are represented. Everybody, all of us have different backgrounds. So that's one reference sort of from this course. And of course, my point of view is, because I don't know the other stuff well enough, is matrices, linear algebra. I look at these as I'll just look at these as problems in linear algebra. We're looking for that solution U hat, and new data comes in, and we're looking for the change. So we have a U hat old from an original set of data. Some new comes in. I have to update it, and I'm looking for the formula. So that will be sort of straightforward matrices. I guess I'm hoping that's a language that almost everybody speaks. I hope. I mean, at least it's like more. It's not Esperanto, maybe, but it's sort of. You don't need to be a specialist in these areas to deal with the matrix formulas. But I have to admit that once I see those formulas, or once we see them, we can figure them out by regular matrix methods. There's one identity, one matrix identity that I've mentioned before, and now it's going to come into its own as the most important identity of, and sort of most important non-obvious matrix identity in the world. And so that's what will get used. But if these other people who knew the different ways to look at it hadn't derived, if Kalman hadn't derived the Kalman formulas, I have to admit I wouldn't have been able to get to them. So it's sort of those insights are crucial. And so I should mention some authors, and you'll know others. One recent book that's, I think, especially clear is by Brown and Huang. I'll just maybe put these over here. Brown and Huang. And it has the words applied Kalman filtering in the title. An earlier book that was edited by Gelb and came from nearby is also highly recommended. And I always enjoy the writing of Tom Kailath, who has a number of books about Kalman filters. In fact, I think a couple of new ones. And here's a very old one, Lectures on Wiener and Kalman filtering. So I didn't know what Wiener filtering is either. But it's lots of insights in Kailath's book, lots. So those are a few of the possibilities. Okay, so that's some comments about books, very incomplete. And I'm happy to know of others, always. I'm beginning to get emails of all sorts now from you, and I'm really appreciating it on topics and on applications. For example, one application that I'd like to follow up that's been significant at Lincoln Lab, Bob Nichols got me connected a little bit is this STAP, the STAP. And so I'm starting with an article from Lincoln Lab Journal. And what was the key issue in that article? It's exactly what we talked about last time. The samples. So this is part of the recap. Then this is a recap of the QR part of last time. In Janice McMahon's very nicely written paper on STAP, the central problem is to deal with, to solve a linear system where the coefficient matrix, let's call it R to follow her, comes from taking many samples. So this is the coefficient matrix, the sample matrix, you could say, coming by taking many samples from radar data at different frequencies, different Doppler, lots. So X is a very long vector. This is probably a full matrix. And what she concludes is that to use orthogonalization in parallel is, and using heavy computing, of course, is a way to go. I'm going to hope to meet with her and speak more about that. Can I also that's just a touch of what I hope to come back to. And can I also just recap one little point recap the SVD, just to say again what it tells us, just most directly. So it's most direct of this factorization U times sigma, totally different sigma. Oh boy. Applied math is running out of letters, even with help from the Greeks. This sigma, of course, this is the orthogonal eigenvectors of AA transpose. Then they're not eigenvalues, they're singular values, and then with a lot of zeros. And then the orthogonal eigenvectors of A transpose A. So maybe there are n of those and m of those if it's m by n matrix. And R here is the rank of the matrix, the number of non-zero eigenvalues of A transpose A, the number of independent, the crucial number, the number of non-zero eigenvalues of AA transpose, the number of independent rows in A, the number of independent columns of A. It measures the true size of A, because the rest of A is sort of zero if we look at it the right way. It's known from these. And now, so that's the SVD, and I just want to point out what we see from there. I could write that as a sum of multiplying column times number times row would be U1 sigma 1 V1 transpose. That's like the first piece. And then the second piece would be U2 V2, so on. And the last piece would be UR sigma R VR transpose. So the beauty is, this is the decomposition of the matrix A. We're talking about A. Everything here is the matrix A. So what do we learn from this? Usually, sigma 1 is greater equal sigma 2, greater equal, greater equal. We usually put them in descending order. So this is sigma max here. And this is sigma min, apart from some possible zeros. So this piece tells us the most important part of the matrix. For example, in images, my matrix I could think of it as an image, right? If you give me an image, I could just divide it into pixels, and then for each pixel, I'll say put the gray level, and that gives me a matrix of gray levels. So let me take a possible application. A is a matrix of gray levels, of pixels. Okay. So that's got n squared, or m times n pixels, m times n entries in the matrix. It's a giant matrix, and I want to compress it. What's the good way to compress a matrix? Well, this would be a very nice way. If I do the SVD, then, and keep just this part, say that's a very simple piece to keep. It's a rectangle, m by n matrix, but it only needs m components of u, n components of v, and one number sigma. And it's keeping like the biggest piece of A. We could probably recognize the image from one or a fraction of the total number of pieces, right? If we had an m by n matrix, its rank might be m or n. No reason why it wouldn't be full rank, and that might be enormous. But if we kept maybe 10, the largest 10 pieces, we could recognize the image. So the SVD is somehow taking your matrix and separating it into the natural building blocks. The building blocks are rank 1, column times row, and they're multiplied by these numbers that decrease in order. And so this sort of tells us something about A inverse, how difficult it is, and this tells us what's important about A. And the difficulty is, as I was discussing before the class started, the difficulty is if we have a lot of this to do and we have to do it a lot in real time, then we have to consider how quickly can we get the SVD. I'm beginning to think like Lincoln Labs needs a department of numerical linear algebra, because the problems you're facing are these questions of efficient calculation of very, very large systems. And do you do it on, do you use QR? What do you do? Or do you use elimination? Do you do it in parallel? Do you do it on what processors? How to make that efficient? I mean, it's really a central issue. And it's certainly a part of these lectures. It's not the only part. But I'm happy to, let me say this again, I'm really happy to know what the problems that are arising are, and especially if I'm able to translate them into a familiar language and sort of identify, well, what is the underlying problem here? Is it, with SVD, we have to say clearly that it's, even though people have found very good algorithms for it, it's still a heck of a lot of work. Basically, you have an eigenvalue problem to do. And eigenvalue problems take, that bit more time than QR or LDL transpose, LU, elimination. Okay, any comment? You feel free to make a comment, because this is like preliminary before I launch into today's lecture. Any or comments offline are totally welcome. Okay, ready to go on least squares. Okay, so this part I take as known. We got to that either by a minimization of the error, b minus au squared, or geometrically we got to that by a projection of b onto the column space of A. But we got there. It's on the videotape, so I don't. It's on the record. Now, I'm ready to discuss point 2. Why the weights? Okay. Now. Okay. I would like to know why these are the appropriate weights. The sigma. So let's remember what sigma is. The covariance matrix. Sigma. And if I'm trying to remember what it's the covariance of, I might put a B to remind myself. It's our system is coming to us with noise. So we get AU equal B, say, minus noise, E. And of course, we don't know exactly what that noise is. But we may know sort of what its variance is, what its expectation is. Is the average noise 0? Let's say it is. Because if the average noise isn't 0, we'll subtract off that average to get noise that has average 0. So I'm going to always assume that the expected value of E, of this error, B minus AU, is 0. That doesn't mean we expect it to be 0. We expect its average to be 0. It's more as likely to be plus as minus, roughly speaking. But if we square it, then we get this is the expectation, the average value of the error squared. So essentially what I'm going to put in here is E squared, right? The expectation of E is 0, and now I'm looking at the expectation of E squared. But E is a vector. We've got here M measurements, MBs, M errors. So this is and those errors, those M errors from the M measurements may be independent and identical, just all and very frequently. So we might use the word white noise or something for the error in that case. Or they might be correlated. So this matrix tells us, and you've seen it before, that's the covariance matrix. So let's just look at a typical entry. The ij entry is the expected value of the ith error times the jth error. And independence means that the matrix is what? So what's the matrix? So independent observations would mean independent errors would mean what? That the matrix is diagonal, right? That when I is different from j, there's no connection between those two errors. The joint probability is just one probability times the other, in which case we can like separate this into two integrals, and this is our assumption that the expectation of a single one is 0. So we get 0 times 0, we get 0. So independent errors would be sigma ij would be 0. Okay. Yeah, is that, or this would be 0 anyway. Yeah, the ij entry. Independent errors, you said it better. Diagonal sigma. And identical errors, what would that mean? Because you often see these words. In fact, they get abbreviated to II because this is an assumption, this whiteness assumption is made so often. And when they're identical, what would that mean? right, and for our matrix that will mean that sigma, yeah, it's just a multiple of I. Sigma equals some whatever, this common sigma times I. Right. So that very often we assume that. And just to mention, you can always look at what we can always change variables, whiten the errors. By a change of variables, if we put part of this sigma into our problem, the effect is to whiten the errors. In fact, if I put square root of sigma in here, that will have that effect. So I can get to that if I want to, but now I better say something quite important that looking ahead. We aren't going to assume that all our errors are independent or identical. So I'm not going to assume that sigma is so simple. But when it gets to recursive stuff, so that sort of things are happening, you know, we have some information and then we get some new information. Then I will be assuming that the sigma for the old information and for the new are independent. I'll assume that the old errors and the new errors are independent. So that typically, just while I'm discussing sigma, imagine I hope you're imagining a situation in which maybe I better start writing this recursive. Now I'm combining these discussions here. So in the recursive stuff, what's my problem? I have there's old data and there's new data. And my U, it's the same U. So I could, maybe I have one set of measurements where the coefficient matrix is some the old guy. And then a second set of measurements where of the same U, so it's the same U, but new errors, new measurements, and therefore new errors. And what I want to do is I want to solve that problem, following all the rules, but getting the answer in this form. So the idea is this problem should get me, if I do it right, could get me an answer in this form. But I will have to assume, to make this come out well, I'll have to assume that the old errors and new errors are not correlated. Okay, so the sigma for this like combined problem, the sigma combined will be a sigma for the old errors, no correlation to the sigma for the new errors. Do you see what I'm saying? I won't be required to assume these are diagonal, nor will I required to assume that they're the same in any way. In fact, we might have 4 old measurements and 1 new one, or 4,000 old measurements and 10 new ones. It wouldn't even be the same size, but you see that what those zeros are saying is that old and new errors are not correlated. Okay, good. So that's some discussion of sigma. But now let me come back to this weighted stuff. Why do we, so I'm now coming back to weighted, not ready for recursive yet. I'm trying to identify what's our equation. Then I think about how to solve it recursively. But why is this is our central equation of the whole lecture, absolutely. So I've made a specific choice of these weighting matrix, of that weighting matrix, and and it will seem a reasonable choice to you, that we sigma, a small variance, so I'm repeating what I've said back in the least squares lecture. A small variance means small errors, reliable measurements, so we weight those more heavily. So small variance, and then taking inverses means heavier weight. Fine. But why is this exactly the right weight? So that's one point. Why is, I mean, it's sort of the pattern is reasonable to weight the more reliable measurements with smaller errors, heavier weights, but that does it just right. And what is just right about that? And then the other key point is that in a lot of problems, it's not just U hat, the best parameters that we're after. We're after also some information of how reliable they are. How reliable is U hat? So input is measurements B and their variances, sigma B. What's the output? The output will be U hat, the best estimate of the parameters, and the variance, its variance. How reliable is that? And there's going to be, of course, a connection between these. And but the formula for this is it may be more. This may be more important than that. Is what I'm trying to say. This thing comes from a specific experiment that gave us a specific. We made one run, one sample. We got some B's, some measurements. We computed U hat. If we ran it again, we would get a different U hat. So then you naturally ask, well, wait a minute, I can't just run it forever. What are the statistics of U hat? They tell us, like, how good is the experiment before we run it. And that's the information here. So this information is central. Okay. So now the beauty is, and in many cases, many formulas involve the inverse of that. So can I introduce a symbol for the inverse of that matrix? I'll let P be the inverse of this sigma U hat. It's the inverse. Is that okay? I'm introducing a letter for the inverse matrix. Okay. So that if I know, to know P is to know sigma, and to know sigma is to know P. One's the inverse of the other. Okay. And it just happens that a lot of formulas come out especially nice for the inverse, P. And, okay, right. All right. Let me see if I can get, I want to get the main formula here that connects this to this. Okay. Let's see if I can. All right. Let's see if I can see. If I look at this equation, it gives me U hat in terms of B in a linear way, right? U hat is some L, some matrix. So I can, if I talk about formulas for a moment, U hat is, if I just read all that stuff off, it's this A transpose sigma, so that's sigma B inverse A inverse. Put that all over there times A transpose sigma B inverse times B. And for convenience, I might recognize that that's some linear, some matrix applied to B. Okay. And now the reason that helps is that if I'm interested in And as I certainly am interested in this sigma u hat, so what's sigma u hat? What's the covariance matrix for u hat? It has to be the expectation of of the correct u with no errors minus the u hat, which came from B that included errors. Oops, not the transpose there. If I want a column times a row so that I get a matrix. Good. Okay. Now, can I just see what's going on here? I claim that this is my error in U, and the error in U is related to the error in B by L. So this I would like to see as the expected value of L E times LE transpose. Right? To go from my inputs to my outputs, to go from B to U hat, I'm multiplying by L. But what happens to the error covariance matrix when I multiply by L? Okay. So, the point is that when remembering this is an expectation of something, I'm multiplying it's the sample values times the probability of that sample. But everything here is linear, and L is a fixed matrix, so I can bring it out. This is L, bringing out on the left, expected value of E transpose times L transpose. Do you see that? Just the usual parentheses. That's L, E transpose. Looks like a crossword puzzle. L transpose. Okay. So all I'm saying is I can bring the L and the L transpose out of the expectation, because when I multiply these values by probabilities, L is fixed. L is the same. Okay, and what's this here? That's sigma. That's sigma B. So this is sigma B. Okay. So, actually, it's our... No, wait a minute. We could figure out what this is. We know what L is. Now, this is where I feel like a typical bit of magic in these formulas is going to happen now. I'm going to put in this awful expression for L and see what I get. What I'm doing now is totally standard and maybe familiar to all of you, but I think I better take this last step. Can I just say, okay, I'm claiming that this is the right L to choose. Well, Gauss said it was, so who's going to argue with Gauss? Okay, so he says that the right L to take is sigma, is the right C to take is sigma B inverse. Okay, so can I put that L in here? Could you do that multiplication, and do you know what we're going to get? I'll make a little room to do it because L is a little long, but okay, here comes L. Okay, so I have A transpose sigma inverse A, all inverse, times A transpose sigma inverse. That's the L finally. Okay, now comes the sigma. Sigma, I'll just write sigma, skip the B, times sigma. And now comes, I need more room, for L transpose. Okay, this formula will finish before the board does. Now, that was L. What's L transpose? Sigma, by the way, of course, is symmetric. Sigma, of course, is symmetric. So when I transpose, I don't have to worry about transposing sigma. A, of course, I do have to. And this combination is symmetric. So transposing that, no effect. Okay, so now I want to transpose this whole thing in the opposite order. So I transpose that, it's just sigma inverse. Transpose that, it's an A. Transpose that, that's symmetric, so it doesn't change. A transpose sigma inverse A inverse, and what have I got? So this is following all the rules. And notice, well, there's a sigma inverse sigma identity in the middle there. Then there's an A transpose sigma inverse A, which I'll just put parentheses around to call attention. And what do I have? I've got this inverse times this thing times the inverse again. So this knocked off this and left me just with this. Is it all right if I just... That's the answer. What a beautiful answer. That the right choice of sigma, the right choice of the weighting matrix produced a beautiful answer for the variance in the U hat. And the beautiful answer is this, is the inverse, is P, is our P. That's the crucial matrix then. In fact, that's like the most important thing, output. So that the most important output is that sigma U hat, which we finally identified as sigma U hat, we finally identified as our matrix P. Is that right? Let's see. This was wrong. Just fortunately, I get to erase it. I meant P to be exactly this matrix that we're, the crucial matrix for us. P is A transpose sigma B inverse A, all inverse. That's the key. That's the beautiful matrix in the whole subject. And, I can't help saying, this is the inverse of our stiffness matrix. Those early lectures were about this matrix, right, and its inverse. And now we're meeting it as the central output, that the inverse of the stiffness matrix, as the central output, sigma U hat, it's the variance of the error in our estimated parameters. It's fantastic. And, well, there's one more central point. You remember what was special about those matrices in the beginning of this course of lectures? They were tridiagonal. They were tridiagonal. And that came for the line of springs because each spring was just connected to one spring below and one above. But springs here were not connected to springs 10 down, or we wouldn't have had tridiagonal matrices. All I want to say is that the most important word that's not on this blackboard is tridiagonal. I'll have to qualify it. For those first lectures, it was normal tridiagonal matrices. Now we're going to have block tridiagonal. That's the central thing that makes the whole Kalman filter process work, is that the key matrix in there, this matrix in the giant process, is block tridiagonal. That's I can't overemphasize that. That's the key to all the matrix formulas and to the recursion and to everything that's, and you can see that it's lots of applications are block tridiagonal. The new state comes from the old state, but it doesn't come from 10 old states, or it doesn't go all the way back to the very beginning state. It's connected to the previous state. And it's like, we have a differential equation or a difference equation connecting new state to old one. I'll come back to that in the second lecture, of course, when we really get to that. Okay. I just didn't want to... what I can try to do in these lectures is to highlight what seems like to me the key points. We're going to have formulas, and I won't get them all on the board. But those can be looked up. those will be in this chapter that goes on the web, and there are many other descriptions of them in the references, and I haven't begun to give all the references. But the ideas are always not so many, and one of them is block tridiagonal. They're blocks because B new in this recursive stuff, this is a block of B's, this is another block of B's, this is a block of A, this is the rest of A. This is the block picture. Do you want me to write that as a block picture? It's, the block matrix is A old, A new, and it multiplies U. And the U is not changing length. If we have a newer and a brand new block, in the recursive setup, we're still keeping the same U. In the Kalman setup, we're also getting a new U and a newer U and a brand new U. So that's the difference here. That recursive, you could say it in matrix language. Recursively squares, we're adding new rows. In dynamic problems, we're adding new parameters, so we're adding new columns too. So we're adding new rows and columns. So shall I write that down to get it on the board? Recursive, this stuff is new rows in A, and the dynamics is new columns too. New unknowns. Okay. But this lecture is about new rows. It's about this problem. It's about this problem. So now I'm ready to turn to that problem. But first, I didn't make the most important comment about this. I've never written such a long equation, I'm sure, as this one for sigma u, which has turned out to be P, which turned out to have this neat answer. What's the point I haven't made, but it's established in the textbook, is the reason for this choice. The reason that choice is the right one is that it makes this matrix, P, as small as possible. We get the best estimate in the sense that the variance is the covariance matrix is as small as possible by making this choice of sigma. This choice of C. By taking that particular weighting matrix, it produced this answer, and we couldn't have got a smaller. We couldn't have got a smaller sigma u than that. And that's one way to say why it's best. So there's an optimal property of this weight, and that's one way to justify the choice of that as our weighting matrix. Okay? Now, I'm ready to tackle this recursion. All right. So what's the idea? We solve the old problem, then we get new measurements. We have new part of a corresponding new part of the matrix A, and I want to solve the problem again. And the point is, I want to solve the problem again. I don't want to start from the beginning. That's the recursive idea. I would like to be able to say, I would like to be able to use the calculation already made. So I would like to have an update formula of this type. I would like to see the best U for the combined system as the best U for the original system plus some matrix, and that's going to be a key, this Kalman gain matrix, multiplying this quantity. Now, does that seem like a reasonable goal? Before we reach it, let's see what we're aiming for. And what would happen if these new measurements were a perfect repeat and this was a perfect repeat? If A new was the same as A old and B new was the same as B old, so we just ran the experiment twice, or just copied the answer and didn't notice or something, what would we expect U new, the best U to be for the combined system? It'd be the same, right? And you see that that's what would happen with this formula, that U new would be U old plus this would be the best. Is that right? We would learn if well, maybe I'm saying it a little. It should be saying it differently. Yeah, that the best that if our I should have, so I have to wipe out part of what I said and say it differently. Although what I said would apply, but what I wanted to say was, if the new measurements exactly, if this was 0, we wouldn't make a change. Right? That's you see what I'm struggling for here. That if our old measurements exactly gave us perfection in this new system, then we wouldn't want to change, of course. But if they don't give us perfection, then this is called the innovation. This is the new information. This is the innovation here. And we hope that there should be some matrix that multiplies that innovation to give us the delta U hat, the correction. Okay, could we just derive this formula? That's what I plan to do now, is just derive it from first principles. What do I mean by first principles? I mean that I'll write the answer to this problem, and then I'll manipulate to put it in this form. Is that all right? So that's the goal. So what's the answer to this problem? Okay. So we see the problem here, and we know the equation that we have to solve, and we've decided that sigma will separate into two pieces. That's good. You'll see that that's a big help. So actually, what is this left-hand side matrix for this problem? Yeah, let me do this in 2 steps here. Okay. Okay, so I'm about to derive this formula. Okay. Okay, so I've got a whole lot of pieces here. I've got this matrix, and then I've got some changes over here. Let me deal with that matrix first. So I have A, which is A old, A new, times sigma inverse, which is sigma old inverse, sigma new inverse. You see there it was absolutely critical that we had a block diagonal matrix. And now A transpose is A old transpose next to A new transpose. Good. All I'm finding here, oh yeah, all right, let's just do that multiplication out. So what do I have then? I've just got A sigma inverse A transpose old. Maybe if I'm consistent, I write old on every matrix, plus, doing that multiplication, plus A new, let me write the answer down. It's maybe not sigma inverse new A new. Do you see that? Am I doing this right? Am I? The transpose should have been first, shouldn't it? Yeah. Absolutely. Otherwise, all wrong. Thanks. You're quite right. I can't say that I make errors just to keep you awake, but you're right. Well, yeah, but I like to go on record with the truth here. All right. And of course, I was going to see that I was wrong just as soon as I tried that multiplication. So you're absolutely right. It's A transpose old and A transpose new. That's A transpose put together. This is sigma inverse, and this is A. Good. Now I believe this multiplication. Do you believe it? And do you see what it's... I mean, it's quite important to see what happens, because this is like the whole point of the lecture. We're getting new stuff here. Yeah? Yeah, this, you're right. Of course, I didn't correct the last line either. Thanks. It's A gosh, I'm living and dying with A transpose CA here. I ought to get the transpose in the right spot. There we go. Is that all right now? Yeah. Yeah. Actually, the way I would see this is my old columns times rows. I mean, suppose A new is just one new, suppose A new is just one new row. This is like valuable to think of. One new measurement has come in. So we have one new row of A, one new column of A transpose. How much does that change this A transpose sigma inverse A? It changes this just by the column times the row, times, it would just be a one-by-one number in what I just described. You see, I'm multiplying columns by piece, by matrix, by row. And it just fits. Okay, so that's the total. Okay, you see, all right. That better be okay, because I've got now. All right, now so I'm going to have to. You'll forgive me if I depend on the author for help here. Okay. 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 Right. Okay. Now, let's see. Here I'm talking about this will lead to an update of U hat, this update of U. But I haven't written in. Can you maybe tell me what it is? What's the update formula for P? The two outputs are U hat and P. And we're looking, and we're going to write down the right expression here for the update in U. But we darn well have to be able to write down the right expression for the update in P. And what's that? What's the new P? What's the new sigma U hat? Here's P. Well, this is a case where it'll be easier to write the update in P inverse. In this matrix without the inverse, I'll use, so P inverse is our A transpose sigma inverse A. Can I poke this up here somewhere? Just as a reminder, P inverse is A transpose sigma inverse A. It's what we just figured out, actually. So I've really, this says P inverse, this formula that we just got says P inverse new, that's what we were computing, is, now what is this, what is that quantity there? That's P inverse old. So P inverse, no, I shouldn't say new, I should say combined or something. P inverse combined. Or P1 inverse, yeah, I'd be a lot better if I just used 0 and 1. For 0 for old, 1 for new. I guess there's a value to having numbers in this world. Okay, so P1 inverse, the combined, the one that, right, is, according to this formula, is P, the old one, inverse, because that's P inverse, plus this correction. That's the A new inverse, A new, if we're calling 1 for that, transpose, sigma inverse 1, A1. That's the update formula. So that's the update formula for this crucial quantity P, or in fact for P inverse, what we just found. So do you see that actually as we proceed, it often happens that we figure out the update in the P, because P inverse is the matrix here that leads us to U. It's, remember, U hat's got this, all this stuff here is P in there. So if it's no surprise that updating P is an important step toward the update of U, and an important step on its own. Okay, now I'm ready for the update in U. Okay, so what is U? So U combined, U1, the answer for the combined problem is, okay, well, let's see what it was here. It's P1, that's all this stuff, times A. What A is that? That's both A's, isn't it? Yeah, that's the combined A and the combined, right? See, have we got it? This is now, I'm looking for, yeah, what's in here? Okay. Is this part, which is, if I write B as B naught, B1, and I write sigma inverse as sigma naught inverse, sigma 1 inverse, and I write A as A naught, A1, I've got two pieces. I've got A naught transpose P naught inverse, oh no, sigma, yep, sigma naught inverse B naught, that's the old part, plus A new transpose sigma inverse B1, the new stuff. Okay. That's our exact formula. We haven't simplified it all. This is what we would have to do if we don't use recursion. This is the answer if we just tackle the new problem, the combined problem, without paying any attention to the work we did before. But now we want to use that work we did before. So what did we achieve before? We figured out P naught inverse before. And we have an update formula for P1 inverse. Okay, and we can, so I'm going to, this update is going to get plugged into here. Okay, why don't I go to the answer? I think that's reasonable, because it's just 2 or 3 steps that lead to this final answer. And I think the crucial thing is to say what is K. And let's complete the lecture with that. So if that's all right with you, if I just proceed systematically as the exposition does, this is page 146 that I'm using. And let me just write down what this Kalman gain matrix turns out to be, because that's the crucial quantity. It's P1, the updated P, A1 transpose, sigma 1, the new bit of A, the new bit of sigma, and then the combined and the updated P. That's the Kalman gain matrix. And that's what makes this formula correct. And I feel I've covered the board and asked you to watch a bunch of matrix steps. On the other hand, what worries me is this was nothing compared to Kalman. Because we only updated, we only had new B's and new row in U, but not new column. So the next lecture can only get worse. But I'll probably shortcut it by again emphasizing that this is the thing to remember. What are the inputs? What are the outputs? The formulas, clearly, it's not essential to. We couldn't try to memorize or even reproduce all of them. But what are the inputs? What are the outputs? And then what's the problem? What's the goal? And here was the problem of this lecture, which I'm going to call it quits now. And then the second lecture, shall we, well, let's say start at 3:30. Okay, 3:30 for the second lecture. I've learned that a guy named Eric Mazur from Harvard, who's maybe the outstanding person in science education these days, is speaking just right now in the auditorium, is it? Yeah. So I'm going to at least go and see what he looks like. And be ready for 3:30 Kalman filter. And ready for advice from you offline, in person, or by email, in between. Okay, see you at 3:30.
What was that page 146 of?
The book you have. That book, right, yeah, that's right. Page 140, right. And then